Okay, so today we will talk about conservative forces and the corresponding potential energy functions that go with them. So in physics, there is for every force that is a conservative force, there's a corresponding potential energy function. So to get that, you will take the derivative of potential energy with respect to position. Sometimes you'll see it written as du dx if position is measured in x, or du dr if we're measuring position in r. So if this is our force function, then our potential energy function is going to be negative integral of f dx. And I really want to emphasize this is only true for conservative forces. And so what do we mean by conservative forces? A conservative force is one where we only care about the starting and ending points and not the path of that the force went. So an example of that is a conservative force is something like gravity or spring forces. And so both with gravity and spring forces, you can always, like gravity or spring will give back the work done against it. While something like a non-conservative force, so that is something like air drag or friction, anything where, let me just write that down real quick. So that's air drag or friction. And these are any forces where the energy is converted to heat and you cannot retrieve that. Okay, so I want you now to think about what concepts we have studied this year where there's a force and corresponding potential energy function. Go ahead and pause the video, give yourself a couple minutes to think about this, and then you can check back in. Okay, so now that you've had some time to think about it, I'll go ahead and write down some that I thought of. So we have spring force is a great one, where that is negative kx, and the corresponding potential energy function to go with it is 1/2 kx squared. Cool. Yeah, so you just take, to go from force to potential energy, you just take negative integral of the force with respect to position, you get it. Another good one is force of gravity is, we could say if we're dealing with direction, negative mg, while gravitational potential energy is going to be mgh. Or our big potential energy, force of gravity equation, gm1 m2 over r squared. And then you can get for the corresponding potential energy function is negative g m1 m2 over r. Okay, so we're now two problems dealing with conservative forces and a corresponding potential energy function. So for the first one, okay, we have a potential energy function given by this. A, B, and C are constants. What is the expression for the force on the particle? Okay, so first thing I'm going to do is I'm just going to write down the two equations that we know we're dealing with. So we have F equals negative du dx, while u equals negative integral of f dx. So in this case, we're trying to find the force. So we want to find the force. I'm going to use this equation that I went ahead and circled. So F equals what? Negative du dx. Great. So now I'm just going to go ahead and plug everything in. And I always write things down. It always helps me avoid silly mistakes. The potential energy function is cx cubed minus bx. Cool. So now I just get to take the derivative with respect to position. So cx cubed, and I can't forget I have the negative in front of everything, so that's going to be 3cx squared. The derivative of negative bx is just going to be negative b. Cool. Now I can just go ahead and distribute the negative sign, so we have negative 3cx squared plus b, and that is our answer. Okay. So we have one more problem we're going to solve together. So, okay, we have a nonlinear spring. So it's not something that's kx. It is now, in this case, f equals 40x minus 6x squared. Cool. And we want to find the change in potential energy when the spring is stretched 2 meters from its equilibrium position. So just to start, I'm going to write down my equations again. So I have f equals negative du dx, and u equals negative integral of f dx. So in this case, we want to find the change in potential energy. So I am going to use this equation right here. I'll go ahead and write it out and then start to plug things in. So u is negative integral of f dx. So we know with integrals, we always have to have the limits on our integral. So it's stretched 2 meters from its equilibrium position. So it's starting at equilibrium, which we know is x equals 0, and it's going to 2 meters. So x equals 2 meters. Cool. So now I'm going to go ahead, plug everything in. So f is what? 40x minus 6x squared, integrating with respect to x, from x equals 0 to 2. Perfect. So now let's go ahead and take the integral. So let's see, integral of, sorry, I should put the negative sign out front before I do any silly mistakes. So this will be what? 20x squared, and then this one will be 2x cubed, and we're going from x equals 0 to x equals 2. Perfect. So now we just need to go ahead and plug in our two limits. So we have 20 times what? 2 squared, take away 2 times 2 cubed, and then this is take away, let's see, 20 times 0 squared, take away 2 times 0 cubed. Cool. And then we go ahead and crunch some good old math, and I got 64 joules on the inside, but then we have a negative, so negative 64 joules. Very nice.